Good morning, and so we have been doing parallel computing with various platforms, right? So CUDA was in C. You could also use C++, but please keep in mind that malloc, CUDA malloc, all that has to be there in C only. That's C syntax. Okay, but CUDA does have support objects. If people are aware of objects, so C objects can be used, C++ objects, but we are not going to do that in this class. Okay. Then we did CuPy, which was simpler. CuPy, you do not worry about allocation and CUDA, malloc and all that. So, it is convenient, but the problem is that you do not get as much speed up. We get good speed up, but you do not get as much speed up. Now, we will work with Numba. Okay. This is third platform for using GPU. I will do one more after this on OpenACC. So, let us just write that CUDA was what I did, then CuPy. So, this is with Python, this is with C, C++, and also with Fortran, which I do not know Fortran, but a lot of people use Fortran. So, but anyway, we will have to stick to some part of the paradigms, we can't do all of it. Then today I am going to do Numba, which is Python based. So, Python CUDA is so there were earlier there were quite a few other platforms which are not popular these days, at least according to me, Cython, PyCUDA. Okay. So, they CuPy has adopted quite a bit of those frameworks, and this more modern version, but you may see significant literature on PyCUDA and also Cython. Cython is C plus Python. Okay. Some codes may be there in Cython. So, these are useful, there are still people probably are using it, but we are, I think this is more modern, this last developed over last 5 years, and Numba I think is a good platform. Okay. And then we will do OpenACC. Okay. So, you have C code or C++ code, you can use directives, sequential code can be put in GPU and you get a good speed up, well 50 also, okay, not like CUDA, but you get 50 or 100 speed up with OpenACC. So, there is another platform called OpenMP. Okay. So, but OpenMP I will not do GPU part, I will just do OpenMP later. I hope to finish Numba and OpenACC before after, well, today and on Friday. We work with Numba, right. In fact, Numba was great for sequential code. You just say JIT ampersand, this is a directive, and it was converting to C code, optimized C code. So, that is what here also. So, what Numba does is converts to CUDA, converts to basically CUDA code. In fact, it will do it in the background, you do not need to worry. In fact, that is a paradigm. I mean, you do not want to bother yourself with all these pointers and block and threads. So, idea is let somebody else do it. Okay. I mean, I will just write simple code, and so that is the idea. So, from Numba import CUDA. So, it will create a CUDA code in the background, and if you say print CUDA dot GPUs, so print what are the GPU devices. So, it says manage device 0. This is there in my Colab, you can just click and play with it. So, manage device 0, so this is one GPU and its name is manage device 0. Then you remember we need to copy to from host to GPU and vice versa. So, this is a syntax. So, this will create an array, it will create an array, it will create a Python array. So, a CUDA dot device array. So, where will it create? It will create in the device means GPU. Okay. Please remember, host is your CPU plus memory, and device is GPU card, and there could be more than one device, but in this course we are staying to one device. Okay. But the multiple device you can still use, but then you have to do MPI across device. Okay. We may have, in summary I will just say a few words about that. So, this will create a array, device array. It is like a Python array. So, device array bracket 0 comma 0, you can do whatever standard Python stuff, or you can copy a this is NumPy array which is there in host, which can be transferred to device. So, CUDA mem copy, okay, this mem copy from host to device. Okay. And how do I run a kernel in Numba? So, the syntax is you put the kernel, my kernel, this is name of the function which will be running in GPU, and you have to give you the block and thread. So, this needs how many blocks and how many threads and data. So, if you know how to run CUDA with C, this is easier. You do not need to worry about many things like pointers and blocks. Well, here you need to worry about something about blocks. So, it is in Python, okay. Instead of C you are using Python, but you are still using GPU. I have not tested how fast it is compared to CUDA. That is something I would request someone to do it, or some group to do it. We would like to see how Numba is doing compared to standard CUDA. So, the thing is CUDA with C and Numba with Python, but Python things are just going into device. So, I am here in this example I am multiplying an array A with 2, doubling the array. So, I forgot to tell you there is a web page where I took quite a bit of I should probably highlight this. This is a page, which is a good page. Numba also has its own description, but that is not very good at moment. I think the developers are also very busy. They are trying to develop the code, and so documentation takes a back seat quite often. So, documentation on CUDA with on the Numba platform is not great. So, I took this website and I took the examples from there. Okay. So, my function, which is the this is a Python function. Okay. So, this function will double the array. Well, I think here something is missing. I did cut. This should be IO array pause. This is missing here. This is my function def function name IO array, and so position is a variable. So, what I am doing here, CUDA grid 1. So, CUDA grid is going to come from here. Okay, CUDA grid will come from here, and it basically CUDA grid is if 1D array, then it will be 1 and it will give the index. So, it is a thread index basically. Okay. So, this is the idea is again the same. So, the code is divided into blocks. I mean, your GPU is divided into blocks, and blocks are divided into threads. So, pose is basically thread index, okay, within your block. So, what is it doing? It is getting the thread index pose, and pose less than IO array size. Okay. So, this is being passed. So, the data is going there, IO array size, and it is just going to multiply. Presently, you are not thinking of dividing the data, this will be done inside. So, this is a standard function, but instead of getting index I is from starting from 0, you have to call the CUDA grid. This is the only difference, right? Otherwise, this function is same as what any Python function would be, multiplying an array A by 2. My array is IO array, right? This is the argument, clear? So, how do I call from host? So, I create a data which is NumPy ones 256. So, it has all 1, size is 256. Then thread per block is 64. So, I am going to create 4 blocks, each block has 64 threads, 64 threads, one more block, 64 threads. Then block per grid. So, so there is a grid, no. So, the how many blocks? So, there is only one grid right now for me. So, so it was going to be data shape 0, it is 1D array divided by thread per block. So, it is going to be data shape will be 256. Whether shape is for any array A dot shape will give you the x direction size, y direction size, z direction size for 3D or 2D, two thing will come. So, this is going to divide, and 256 by 64 is 4. So, indeed there are 4 blocks, 1, 2, 3, 4. Then I am going to call my kernel blocks per grid. So, the way we did in CUDA, blocks and thread, and which data you want to operate on data, okay, and print blocks per grid. Okay. So, this is going to be it will print the no actually well this was what will it print, blocks per grid will print 4 for this example. How many blocks every grid? So, I was doing debugging. You can also print data after this. So, what will be the data after this? Instead of once, it is going to be 2, all the entries will come 2. So, you can run this code, is there in Colab. So, it is HPC, the thing you should HPC underscore GPU, that is your file where you CUDA, Numba, CuPy and OpenACC, everything related to GPU is here. Is that clear? The simple code is also telling you how in Python using Numba I can divide the data into threads, or basically I create blocks, I create threads, I do it like this, and I can use GPU. So, it is in fact pretty nice, no. I mean, code size is basically half of C code, we do not need to worry about include, well there is one include, Numba include, okay. But well I do not know, you have to see whether you like C or Python. So, this is one alternative. So, this one more complex example is multiplying a matrix. So, you have 2 matrix A B and I want to multiply. So, this standard Python algorithm. For big matrix Python will be very slow. So, you can use GPU. So, let us look at the code. So, if I do not optimize anything, straightforward. So, this is my basically slight change in the Python code, standard Python code, and this is multiplication. So, what do I do? So, you can just, it is very obvious. So, first get a row and column. So, CUDA grid 2 will give me the size, row size and column size. It is, please keep in mind, it is divided among GPU. So, I am not using a loop. So, Python normally you will put a loop, no, for I da da da, for j da da da, then k. So, 3 loops. Here there is no 3 loops. So, there are lot of threads and every thread has a row and column. So, this CUDA grid is giving you that index, okay, and data ABC full array is visible to all the threads. In fact, this data is sitting in global memory of the device. So, what I am going to do? So, for a given row, this is a row, in given column, I just multiply this, no. So, this guy goes, you take this column of B and flatten it and multiply. So, this element will be multiplied to this element is multiplied by this element. This figure is not good actually. This size it should be same as this size, right. When I flatten it, so this should be 1 to 1, but it is not well, I mean the figure has bit of issue, but you understand matrix multiplication. So, this particular thread, this thread is going to do that sum, multiplication and sum. So, for k in range, A shape 1, what is A shape 1? Is the number of columns of A, right, columns. row is index 0, column is index 1 in 2D Python. So, row shape 1. So, I am just go for every element of row column and multiply that with. So, row is so k is varying, no, k is varying, this column is varying, multiply this with b of row, but column is fixed. Well, col is column of C, okay. So, this column is column of C, this is column and this is row. So, I am computing one number of C. How do I do it? I multiply the full row of A with full column of B, and that is what is being done here. And once it is done, then so this is a temp variable, okay. Temp variable is collecting all the data, and C row comma col is temp. So, I am just going to store it there. Fair enough, simple, no? It's a bit of work like what you do for CUDA C. You need to understand you are working with threads. So, it is not just straightforward, I put some hash command and I will convert it to CUDA. Sorry, I will make it available for GPU or run it on GPU. Okay. But this code has a problem. What is the problem with this code? Here I am going to access global memory for every time. All this data is sitting in the global memory, and it's not good. Okay. This one thing is to put in shared memory. Also, this data is big, then is maybe, so this is not optimized for many threads. Here, if your data size, if the row and column together is less than 1024, this is a good code. Otherwise, I should divide in blocks, right. If the size of C is bigger than total m into n is bigger than 1024, this is not a great idea, no. This is I should divide in blocks. Okay. CUDA may do it already, and this NUMA can do it, but you can give slightly more hints. Okay. So, in fact, it is also true that if the programmer has something in his or her control, then you get optimized code. If the programmer is clever, programmer has to be clever than compiler, which is not great. Compilers are not great for doing automatic parallelization. That is the aim. Of course, all the biggies are working on it. NVIDIA, lot of programmers, okay, are working on how to make automatic parallelization, but we are not there yet. So, you can make some the two stuff. One is converted into blocks. So, this is slightly refined code where I am converting this into 3 blocks. Okay, this is block 1, block 2, block 3. And now I am going to take this blue block, will multiply with blue block, yellow with yellow, and green with green. So, here also there will be this is part of okay, I mean there will be places which will be blue, well depends where you are. So, you can do it with faster, still not well. I will do one more refinement after this, but I am not doing shared memory yet, but I am making blocks. So, code is a bit longer. Okay. So, the other part of the code, the one function will remain the same except the main part of the code. So, even though I do not write main in Python we do not hardly, well sometimes we write main, but often we do not need to write main, we just go line by line till the end. So, I do not have main here, but I am doing this in basically host. This is done in host. So, what does host do? First take this array A, copy it to device. So, A global mem, B global mem, C global mem is copying to device, global memory. Then let us say that a thread per block is 16 by 16. So, I am creating how many threads are there? 256 threads. Inside it may be working with 1D array, but for us we can use this 2D grid. So, 16 by 16. So, block along grid x along x. So, this variable block per grid x. So, I am dividing A shape 0, A rows So, I divide A rows into threads per block. So, this is let us say 48 this size, then 48 by 16 will be 3. So, 3 blocks are being created here. Okay, so, this will become 3. For this example, this is 3. Box per grid Y. How many blocks should I create in along Y? It is I am creating along column, because column and rows will rows of A will multiply with columns of B. So, this is B shape 1, this is column. I divide this by thread per blocks. So, this again divided. It turns out this is also 48 right now for me. Okay, it could be different, it could be 32. So, then I divide by that 16, so I get 3. Okay. So, I have 3 blocks for B and 3 blocks for A. Okay. So, this and a box per grid will be I am making a how many blocks? 3 by 3 blocks, 9 blocks. So, this is C, in fact C is divided into 9 blocks. So, this block will be converted by, will be created by blue with blue, right. This will be blue with blue. Is it clear or not clear? So, blue will align left and will create all these elements. Then blue with yellow will create what? This blue yellow. Yellow will go and do the blue, and then green with blue will give you this. So, that is how we will fill up the entries. Okay. So, I create 9 blocks. So, basically I am using more resources of the GPU. Okay. So, then I am going to call matrix multiplication, this is a function. Blocks per grid, which will be 3 by 3, 9, and threads per block, which is 16 by 16. Okay. And I pass the arguments A, B, C. So, give this full array, okay, but each thread will decide which number to work on by doing CUDA grid. So, this how will this code will work, and after I am done, then I will mem copy from copy to host. So, this is the thing. So, my result I want to bring it back to host for printing to on a printer or putting in hard disk. Normally put in the hard disk, okay, and I am done. Okay. But this code is still not very optimum. It is not optimum because when I multiply, so for example, this element is responsibility of this yellow and yellow block, right, but still accessing is done from the global memory, which is expensive. Anytime I go to global memory, it is the expensive operation. So, what should I do? Shared memory, put in the shared memory. Cache you do not have access, but shared memory, well, L1 cache and shared memory are together, but user can decide how much to keep for as a shared memory, okay, the one which you want control. Okay. So, we use shared memory in Numba. So, shared memory, so this syntax is very easy. Shared array is CUDA dot shared array, shape type, shape comma type. Okay. And you recall that we need to sync all the threads sometimes, you know. So, CUDA sync threads. So, let us look at the code. So, this is a different array, okay. This is not the same array, it is a different array, but this array I am going to show you how to use shared array. This example I took from the same website. Okay, it is a faster because I am going to use shared array. So, let us look at the code. So, I am going to create 2 shared arrays, SA and SB, and what is the size of the shared array? It is shape is thread per block, thread per block, TPB is a variable. You can use 16 by 16 or whatever you choose. It is not a keyword, but it is often used, I have seen in books. Okay. So, this is my thread per block, this guy. thread per block in one direction multiplied in the other direction. So, this is the full block here. So, same thing for B. So, I create two memory areas for putting the data. Now, I am going to do the multiplication of, first copy it into a shared array, right. I need to copy it, and after copying multiply. So, this part is copying into shared array and this part is multiplying shared array. Okay, clear? So, multiplication is straightforward for Tx and Ty, which is a location. This Tx and Ty will be some location in C. Okay, and I am going to put it there. Okay. So, let us see, there be careful. So, Tx and Ty is the location in, this part is Tx and Ty is the location in the shared array, which cannot be full range. This is 32 by 48, right, if I use 16 as a thread block. So, my array A is I will range from 0 to 31 and J will range from 0 to 47, correct. But what is the range of Si and Sb? For TBP is 16, 0 to 15. For SA and SB it will be 15 by, well, 0 to 15, 0 to 15. So, I need to convert my A columns and rows into SA columns and rows. My, depending on my, so Ty, which is, let us say Ty is 1, okay. Now, so this x, I did not think it through. So, it is going to be x, which is going to come from the global. Okay. So, this is x and Ty plus I star TBP. So, A shape is A shape 1 is 48, 48 by 16 is 3. So, I will range from 0 to 2. So, I am covering basically this part. Okay. So, if I am in the second block, which is I equal to 1, second block will be this one, will I equal to 1. So, where should I go? I multiplied by TBP, which is 16, I should add 16 to Ty to get the location of A. So, SA Ty equal to 1 is from where? It is in fact A equal to 17, this is A 17 for when I equal to 1. So, this is being done. So, basically this is done by GPU and it just filling up. In fact, right now I am not dividing blocks, that what I am not doing what I did in the previous one. This is done by a single block, well, done by a single block of a GPU, and it does it 3 times. So, this work is being done by a single block of GPU, and it's 17 and x remain the same, this x. By the way, how do I change x? So, I need to go to this x after this. This part is we will probably see in a main code. Let us just look at the main code. Yeah, here TBP. So, threads per grid. Okay, I am going to come to this. Okay. So, basically let us just see that is doing it for, we are doing it for 3 times. So, I just take this whole block one by one, but I do it, I am dividing this work into shared memory, so that is faster. This part is shared memory, and then I multiply this one first with this guy with this guy, and this guy with this guy, one at a time, and I am keep adding up temp, then finally copy. Okay. So, this to make things faster. So, basically usage of shared array. Now, let us look at the main part of the code once more. So, this is inside the function. Okay. This will be inside the function. Now, here I am doing in main, this is main. So, A and B are, I create these arrays. So, a number of rows is TBP times 2 and columns are TBP times 3. So, 32 by 60 48 and this is 48 by 1, this 48 rows and 1. I CUDA mem copy, then I create threads per block, which is 16 by 16. Then I create threads along axis. Now, this is what is a tricky part. It is 0 by 16. So, it is going to be, this is 2 for our example, 32, 48, 48. This is going to be 2. Along y will be B shape 1, thread 0. So, thread 0 is thread block is, this is 16 always, but B shape 1 is 16. So, this is going to be 1. So, my blocks per grid is 2 comma 1. Okay. Then I do this operation. So, there are 2 blocks, the GPU has 2 blocks. The first block will do this operation, rows 0 to 15, and second block will do the operation 16 to 31. Okay. So, everything makes sense now. Yes. So, this earlier example, this was done by block, this will be done by twice, well not twice, it will be done by different blocks. One block will take care of the this region, another block will take care of this region. Okay. Simultaneously, that is a parallelism. We do not use loops, but we have threads which will take care of this aspects simultaneously. Is that clear to everyone? Okay, you need to run it and you have to think about it. So, there is no loop here and you just divide the work among threads and blocks and you do it. So, this is similar to C. If you like CUDA, stick to C, but if you like Python and do not want to convert to go to C, you can use Numba. And I do not know about speed ups, but there may be some trade off by converting to, well, using Python, but we need to check. So, I gave 3 examples basically, okay, simple example, matrix multiplication and use threads blocks in Numba. More complex issues. So, basically this Numba is for using CUDA, rather using GPU. In fact, it will convert you to CUDA. Standard Numba converts into C codes for multi-core, but this will convert for GPUs, and we like to compare the performance with C, C++. Okay. Streams can also be created in Numba. We can control memory. Okay. I am not covering it here, and I believe this scheme will be popular in future. Okay, that is my guess. Because Python is going to be even it will become more and more popular. It is already popular, but and automatic parallelization. I think people will be wanting to use more and more GPUs. So, I do believe that Numba will become important tool.